Even at the end of the summer, the river is already flowing at 1,000 litres per second. It makes a dramatic sight as it plunges over this waterfall, which is called the Severn Breaks Its Neck. There are several ways in which waterfalls are formed. The most common one is due to a difference in rock type. Where a strong band of rock lies on top of a weak band, the water falling will erode the underlying weaker rocks. After a while, the inevitable happens. Over time, the waterfall cuts back. Eventually, a gorge is formed. After the waterfall, the Severn's gradient soon flattens out, and it starts winding its way through agricultural land. In flat areas, rivers wander about, forming loops of all shapes and sizes on the valley floor. These are known as meanders. Although they all look different from above, they share the same common features.
As you can see, on the outside of the bend, where the water's moving faster, it's cutting into the landscape, forming that long cliff. But here, on the inside of the bend, where the water's moving much slower, all this stuff is being deposited.
The erosion has left a very small neck on the meander. If we strip the trees away and look at it from above, it's easy to see what will happen next. The fast-moving stream will continue to erode the banks on the outside of the bends. It also erodes the area around the meander's neck. Eventually, the river breaks through, cutting off the meander and forming an oxbow lake. After Shrewsbury, the river drops through the Ironbridge Gorge and swings south. By now, the Severn is flowing at over 60,000 litres of water a second, and although the river's mouth is still over 100 kilometres away, it's only 30 metres above sea level. Surrounded by flat land, floods are a significant threat. In November 2000, heavy rains caused some of the worst flooding since records began. Many rivers, including the Severn, burst their banks, causing widespread disruption and damage.
In the past, people have been quite clever about avoiding these disasters. This is Worcester, and the cathedral and the old town are much higher than the rest of the city. That's because they've been built on a river terrace, out of reach of the floodwaters. Since then, the town has grown, and there's been nowhere else to go except down onto the floodplain, closer to the river. These Victorian houses risk getting flooded every winter.
Building on a floodplain also changes the way the land works, a fact that isn't always understood. When rain falls on open countryside, the ground acts as a big sponge, soaking up a lot of the water. But when the land is built on, the paving and tarmac stop water seeping into the soil. Instead of the water ending up in the soil, it's swiftly drained through pipes into the river. That's okay in normal conditions, but when it's very wet, the extra runoff can tip the balance, causing a river to flood. The situation is really serious, and at the moment, no one seems to have an answer. South of Gloucester, the risk of flooding decreases rapidly because the river starts to widen and it quickly develops into an estuary.
It's one of the biggest estuaries in the UK. At this point, it's already 2 kilometres wide, and south of the narrow point where they built the bridge, it's even wider still. The river here is tidal and has the second largest tidal range in the world.
The difference between the high water mark and the low water mark can be as much as 15 metres. And when the tide is out, huge expanses of mudflats are revealed. Many rivers in the UK, like the Thames, the Humber and the Forth, end in a wide estuary, and they all present the same problem. You need a long bridge to get from one side to the other. Here on the Severn, there isn't just one bridge, but two that carry traffic between England and Wales. South of the crossings, the river becomes much deeper, which means ships can come in. This has attracted industry to the cheap land around the estuary, and the shoreline is chock-a-block with factories and dock facilities.
I'm just surrounded by industry. There's a smelting works over there, several chemical plants over there, an LPG and oil terminal down there, and just over here is a container terminal for import and export to all over the world.
500,000 cars pass through the port each year, and the £27 million refit of the neighbouring Portbury docks should ensure that traffic through the area continues to grow. By the time it reaches its mouth, the Severn is 13 kilometres wide. The river looks like the sea. Having started as a trickle in the Plinlimmon Hills, it has run 350 kilometres. And by the time it reaches the sea, it carries over 9 billion litres a day. Quite a transformation. In the summer of 1993, the Mississippi, one of the most heavily engineered rivers in the world, burst its control banks in one of the most devastating floods to hit the USA. This event brought to a head a question that has been smouldering for a very long time. Can big rivers like the Mississippi ever be completely tamed, or will nature always, somehow, take its course? The Mississippi is over 3,000 kilometres long, draining half of the United States. It's the major river artery of America. 300 years ago, before Europeans arrived, the landscape in the valley was a wetland measuring 100 kilometres from east to west, across which the river wandered at random. During periods of really heavy rain, the river burst its banks, turning the floodplain into a lake. When the rain stopped, the river would often return to a completely different route from the one it had taken before. This was a nightmare for shipping. The average paddle steamer only lasted 18 months before crashing. Without a reliable shipping channel, the transport of farm and factory products was chaotic. The valley's economy in dire straits. Something had to be done. It was the Army engineers who took on the huge task. Their first move was to build what are known as wing dikes out into the river. Built from tough stone, they trapped large amounts of the river's sediment, forming new land, which narrowed the channel down. What happened is what the engineers had predicted. Forced into a narrower width, the river flowed faster and eroded a deeper channel. A much better bet for shipping. But this didn't solve the flooding problem. Every spring, as the winter snows melted, the river did what it had always done. If agriculture, cities and industries were to grow successfully next to the river, another idea was needed. This time, what the engineers did was literally wall the river in. These walls, known as levees, were built along the whole length of the river. eventually offering better protection to riverside developments. But as the population grew, the engineers came under huge pressure to make sure that flooding would never ever again be a threat to people and property. At that point, they really went for it. First, control dams were built to hold back floodwater and reduce pressure on the levees. Second, they changed the map of the valley. Shortcuts were blasted through the numerous meanders. Water was speeded more smoothly downstream. The natural course of the river dried up. By the time they'd finished, the Mississippi was 250 kilometers shorter. Third and finally, the river banks were stabilized with matrices of concrete slabs. It's taken 100 years and £7 billion to change the whole look of the Mississippi River landscape. Then, in the late spring of 1993, the weather over the Mississippi Basin went mad. The border between the warm air from the Gulf of Mexico and cold air from the Arctic got stuck 2,000 kilometers farther south than normal. Along this crucial junction, it rained for weeks on end. The result was a massive increase in the volume of water in the river. Water that in the river's natural state would have spread sideways was hemmed in, trapped between the levees, leading to a frightening build-up in pressure. The river didn't like it. In the end, the levees gave up under the sheer weight of water. Having more or less protected the riverside areas from the Mississippi's average behaviour, the engineering could not ultimately cope with nature at its most extreme. The lesson from 1993 is that the Mississippi will probably do the same thing again. The threat of flooding will not go away. But how could anybody ever say, "You can't build here"? Around 2 million years ago, an ice age began in the southern hemisphere simultaneously in South America, southern Africa, Australia, and here in New Zealand. The same thing was happening in the northern hemisphere in North America, Europe, and Asia. Indeed, in both hemispheres, the phases of the Ice Age were very similar. And so were the changes the ice brought to the look of the landscape. Like many other spots on Earth, the Ice Age, in a way, still carries on here. These are the peaks at the head of New Zealand's Franz Josef Glacier. They're 3,000 metres high, and temperatures are below zero all year round. The mountains are battered by blizzards surging in from the ocean. At this height, year after year, a huge supply of snow piles up on top of the glacier. As it thickens, this fresh snow is compressed under its own weight into ice that will eventually become part of the glacier that's underneath. It's the snow on top that feeds the ice beneath the surface.
It's in winter that the, if you like, fuel tanks of the glacier really begin to build up. It's the 4th of June and there have been 3 major snowfalls already. Let's see how much. That's about 3 meters in the first month of winter.
It may seem unbelievable, but this massive weight of frozen material actually moves downhill. When this force is directed at a single valley, like in the Franz Josef Glacier, the results are spectacular. The ice grinds away at the land rather like a huge chisel, deepening the valley, plucking rocks from the valley sides and from the valley floor. This material caught up in the ice is known as moraine. The moraine, in turn, adds to the glacier's power to erode, deepen its valley and shift stuff along.
It's amazing to see just how much material the glacier is actually carrying. In fact, it's working like a kind of giant conveyor belt. 60 years ago, it conveyed an aeroplane. It crashed 14 kilometers up the glacier and it reappeared from the end 6 years later. The largest natural item being transported by the glacier at the moment came from this huge rock face. For many years, the ice has been plucking fragments from it and shifting them 200 meters downhill, forming this huge moraine right in the middle of the glacier. It looks almost as though the piles have been dumped here by a bulldozer. Not true. It was the driving force of one of the steepest glaciers in the world, the Franz Josef.
At the height of the Ice Age, the Franz Josef was moving downhill at the incredible speed of 6 kilometers a year. The glacier's speed and its length both change according to how heavy the snowfall is on the fuel tanks at the top. It's currently 23 kilometers from the top to what is known as the snout, the spot at which so much ice is melting that the glacier can't carry on any further. Here, water joins the ice as a driving force as the glacier begins to lose its grip on all the material it's gouged out and brought downhill. Big boulders that have been moved a long way by the ice are known as erratics.
And if you need any more proof of just how powerful a glacier can be in terms of eroding rocks and transporting them, then just take a look at this one.
The land downstream from the snout is made up of layer upon layer of glacial drift. Drift being the name of all the different kinds of material shifted by the ice and the meltwater. 90% of the drift below the Franz Josef Glacier came from a rock with the weird name of Greywacke. There's so much of it that it has a landscape all of its own that extends for 25 kilometers beyond the snout of the glacier. Everything here, the plains, the hills, in fact all the relief features are made of glacial drift, all the way to the beach.
But the beach isn't the end of the story, because the drift extends 10 kilometers to the west, out onto the seabed. That's how far the ice reached during its maximum extent, at the peak of the Ice Age.
Typical of New Zealand's South Island, what we've got here is a coastline made of glacial drift and all the physical geography that comes with it.
My favourite erratic in the cliffs is just up there. And I reckon with a couple more storms from the Tasman Sea, it'll be on the beach. Now the rock looks like Greywacke, but I can't be sure. But what is absolutely certain is that it can only have come from one place, the New Zealand Alps.
Throughout the world, the most spectacular effects of glaciation were felt in mountain areas. When the ice emerged into the lowlands, it still covered huge areas of the Earth's surface for around 2 million years. As the climate warmed up and the ice melted, it left behind thick deposits of material that it had picked up along its course, known as drift. In places, the drift is divided into two different types. The first is boulder clay, a sort of thick sludge that was beneath the ice. The second is outwash, a much more stony, gravelly stuff that was carried away by streams flowing from the edge of the ice sheet. Over half the UK lowlands are covered in drift. Near the Norfolk coast, it's particularly thick. Ice disappeared from here 2 million years ago, leaving behind large areas of boulder clay and outwash. 2 million years is quite a long time by the standards of the Ice Age. So in places like Norfolk, it's often not so easy to work out what the ice was actually doing. But here, however, the geologists are sure that something rather special happened.
The line of this hill marks the spot where the ice actually came to rest. It came in from the north, from that direction, and stopped right here. So, beneath the ice, over here, boulder clay was being deposited, which has given rise to land that is perfect for farming. It's what a farmer today would recognise as being good stuff. But what about the landscape over there, beyond the ice, on the outwash?
Well, there's a big contrast. The vegetation is heathland, the soil thin and no good for farming.
Two different kinds of landscape, right next to each other, all thanks to the Ice Age.
In the lowlands, the changes that ice brought to the landscape are nothing like as dramatic as those in the uplands. But in places, the lowlands can often come up with the unexpected.
Like here, on the northern coast of Norfolk. For 20 kilometres to the east and west of here, the cliffs are composed entirely of glacial drift. Not rocks that are local to the area, but stuff that was brought here from somewhere else, by the ice.
If you're into glaciation, these cliffs near the town of Cromer are one of the most famous spots in Europe. It's a 50-metre high slice through several layers of drift carried here by various ice sheets over a period of 1 million years. It's a fascinating insight into the rocks picked up along its course and the unusual landforms that have developed from this strange concoction of material. The cobbles on the beach have been eroded from the cliffs by the sea. They're the best clues as to where the ice came from.
They've all been brought from the north of here by various glacial advances. This one's chalk. It won't have come too far, and it's definitely English. From its colour, this one seems to have a high iron content, but I'm not really sure what it is. And this is sandstone. That'll be English too. This is granite, definitely Scottish, and this is marble, almost undoubtedly from southern Norway, 1,000 kilometres away. What we've got here is a multicoloured Ice Age beach.
One of the last events in Britain's Ice Age was a re-advance about 15,000 years ago of small ice sheets in mountainous areas like the Highlands of Scotland. In many places, the ice wasn't thick enough to smother the mountain range that runs like a barrier through the northwest of the country. In some spots, though, a tongue of ice did manage to force a way across. When the ice retreated 10,000 years ago, what was left behind was the usual U-shaped glacial trough. It's called a breach. There are lots of them in Scotland, and they've proved absolutely ideal as a way for railways to find a nice flat route through the mountains. Harlech Castle sits on the west coast of Wales, overlooking the Irish Sea. It was built in 1289 by Edward I, King of England, and despite several battles, it remains in good condition.
But the reason we're here today has a lot more to do with the castle's geography than its history. This is the Watergate, and the steps I've just come down are called the Way from the Sea. That's because ships used to be able to sail right in here to deliver goods to the garrison based in the castle. That was 800 years ago, but the situation is a little different today.
Harlech Castle now stands over half a kilometre from the sea. It's all due to the processes that are changing the coast. To understand what's happening, we need to start at the southwestern corner of Wales, in Pembrokeshire. This is one of the most exposed parts of the Welsh coast because the prevailing winds are from the southwest. Waves driven across the Atlantic smash against the cliffs, continually wearing them away.
The harder pieces of coastline, like this headland, only erode quite slowly. But the softer bits, like that bay, get eroded much more quickly. And it's this difference between hard and soft rocks that leads to the repeating pattern of bays and headlands.
Although these cliffs are all made of the same material, Carboniferous limestone, the rock isn't uniform throughout. It has weak layers, faults and cracks running through it, all prime sites for erosion.
The erosion is due to several processes. There's hydraulic action, where the crashing waves compress water and air trapped in cracks, weakening and eventually loosening the rock. There's abrasive action, where material suspended in the water gets smashed up against the cliff face. And finally, there's chemical action, where the rock is dissolved by seawater and the rain. And just below where I'm standing is an absolutely stunning example of all these processes at work. This is the Green Bridge of Wales, a fabulous example of a sea arch.
If we go back 5 million years, the coast would have looked like this. First, the sea goes for the weak bands of rock. Then it goes for the cracks in the harder rock, forming first arches and then stacks. This leaves the Green Bridge as we know it today. It's easy to guess what will happen in the future. Not all stacks are formed this way. Sometimes they just get left behind as the coastline around them erodes.
Those stacks will get worn down by the waves and the weather and become stumps, like this one.
Arches and stacks aren't the only structures carved out by the erosion on these cliffs. Here, waves have punched a hole in the bottom of the cliff, and then the erosion has opened up a vertical fault, like a chimney, forming this huge blowhole. The bays left in these limestone cliffs are relatively small. When rock types of differing strengths are placed together, the bays can be much bigger. St Bride's Bay is a good example. It's 15 kilometres from one headland to the other, and it's all down to a difference in rock type. The northern headland of the bay is made up of hard igneous rock. The southern headland is a mixture of igneous rock and sandstone, which is also pretty hard. But in the middle of the bay, the rocks are mostly sedimentary rocks, which are much weaker than the rocks in the headlands. Over several thousand years, the softer rocks have eroded much faster than the harder rocks, forming St Bride's Bay. The sea isn't the only force that erodes the coast. This cliff is made up of an Ice Age deposit of sand and clay. And in places, the top sandy layer seems to have slid down on top of the clay. It's been caused by rainfall, and the process is known as cliff slumping. The sand layer is permeable, but the clay layer isn't. When it rains, the water soaks through the top material, but it just collects in the clay below. As the base of the cliff gets waterlogged, it becomes unstable and collapses. Eventually, the debris on the beach is swept away by the sea, leaving the cliff exposed once more. So far, we've only considered erosional processes, but what happens to all the broken-off pieces? To find out, we have to head north, back towards Harlech.
And here it is. All that stuff that was knocked off the cliffs to the south of me has been ground down by the sea and washed up here as sand and pebbles to form a beach.
Borth Beach, just north of Aberystwyth, is about 2 kilometres long. The sand is on the lower part of the beach, and big waves throw the pebbles up to the top of the beach. But how does it all get here in the first place? The answer is longshore drift. The process depends on waves hitting the beach at an angle, as they do along much of this coast. Let's concentrate on just a few particles. The particles are washed up on the beach by the waves, which, driven by the prevailing wind, hit the beach at an angle. As the water runs back into the sea, it pulls the particles straight back down the beach under the force of gravity. The next wave moves the particles a little bit further up the beach, and so on. The process is known as longshore drift. Even in small waves, you can actually see sand particles in the water. This movement of material means that over time, beaches can change their shape and sometimes disappear completely.
That's why people build these groins. These wooden partitions trap material on the beach and prevent it from being carried away.
At Borth, nearly 60 groins have been built to ensure the beach isn't taken away by longshore drift, but they don't stop the movement of material completely. Inevitably, pebbles and sand get swept over or round the groin and continue their journey. And this continued movement creates another feature common to this stretch of the coastline, spits. Spits are formed where the line of the coast changes, but the longshore drift carries material on. A river estuary is a good example. Longshore drift carries material along a straight line out into the sea. When enough material has been deposited, a spit forms. And there are several examples along this part of the coast.
These dunes mark out Harlech Spit. They've built up because so much material has ended up here. There's not just one line of dunes, but several, stretching all the way to the end of the spit, nearly 6 kilometres that way. The spit itself is massive, almost completely cutting off the river estuary behind it.
The reason for this accumulation is the change in the direction of shoreline north of the spit. There, the Llane Peninsula sticks out 50 kilometres to the west, acting like an enormous groin, halting the onward movement of material. Over the course of nearly